Hello, this is Dylan Moore, and this is Lab 2 for CPSC 4550. And I've already gotten my file uploaded and captured that whole process. And this is what I've got over here after I've applied my TCP filter up here. Um, and yeah, this is what we've got right now. So we're going to go ahead and get started with question 1 over here. What is the IP address and TCP port number used by your client computer? And that would be my computer. So what it is up here is you can find those numbers here, but you can also find that stuff down here in the data fields. But up here you got the initial kind of connection being formed with your sign there. And this is 60633 is going to be the IP address of gaia.cs.umass.edu. Or no, this is not the IP address, I'm sorry. That's the port number for them. But anyways, following the question, this is supposed to be the source for the transfer. We're going to be given an IP address for the source and the port number. So yeah, here we go. Over here we got our source IP addresses, destination IP addresses, and I know my port number is 80, and so I know that on this message right here, my source is 12, or my source IP address is my IP address that I'm using for this connection. So it's 128.119.245.12, and then it says. What is the IP address of guide.cs.umass.edu? And that IP address is, if you go back up here to this first sign message, you can see they are the source, and it's 192.168.1.142. And their port number is 60633, and you can find that right there. But you can also find that down here too. We'll go ahead and click that message right there. And there you go. See, you've got the source port 60633, and the IP address is, let's see, go and explore all the data fields. There they are. Internet Protocol version 4. Source 192.168.1.142. Destination 128.119.245.12. You can see those match up here. Same things, but this is also where you can find that information if you need it. And so there we go. We've got those two taken care of, because as you can see, they just kind of swap after they're sending each other acknowledgments and getting their signatures done. And then you'll go back down here to where you'll get more of a push on some other things. Let's see. So now we're going to go down to the TCP basics. We're going to answer these following questions. The sequence number of the TCP sign segment that is used to initiate the TCP connection between the client computer and gaia.cs.umass.edu. What is it in the segment that identifies the segment as a sign segment? So we're going to go ahead and just stay on that one. That one's highlighted for us. Let's see. There we go. Let's go back to that. And so now we're going to minimize all these guys right here. And if I remember correctly, yep, we can go down here and look at the source, or look at our data fields here, and see, which of course you can see right here, this sign. That identifies it as a sign segment. It's pretty listed over here. It's listed over here in the info. But you can also find that over here with the flags. There we go, there's my flags. So if I drop down flags and you look, it's got a 0 next to everything that it's not identifying as, or that it wasn't identified as, and then down here by the sign it's got a 1. So that is set. So that's also how you can identify this segment as a sign segment. And the sequence number is right here. So sequence number is 0 because it is the first sequence of segments that's going to start. So you have to start at 0 and it goes up from there. It says, what is the sequence number of the SYNAC segment sent by guy.cs.umass.edu to reply to the sign, which is this guy right here, and you can see this is the SYNAC. It's identified right here. And the sequence number for this one is also 0. So we've got that. And the acknowledgement field value in the SYNAC segment is right here under acknowledgement number, and that is a 1. So yeah, there we go. So we've got that. And then the next question is 3, and it says, what is the sequence number of the TCP segment containing the HTTP post command? Note that in order to find the post command, you'll need to dig into the packet content field at the bottom of the Wireshark window. Look for a segment with a post within its data field. So yeah, you can do that, but also after doing some research and learning a little bit about it, if you look for ones that have a push and an acknowledgement, these are more likely to have the HTTP file that you're looking for, the HTTP command that you're looking for, because it's got more length too. It's a longer segment, and that one's a really long segment. But we can go ahead and highlight that and come up here to analyze, and then we could say, there it is, follow the TCP stream. And so this brings up everything, every communication that happens here. And right here you found the post. So we've got our post statement right there, or post command, and all of our other following things that are needed for it. And then our main body of our text here, you can drop it on down to the bottom, and this is your acknowledgement. So you had a push, you pushed all that data, and then you have your acknowledgement attached right here too. And so the sequence number for this one is 1. So that's what the sequence number is for the segment containing the post command. So now we're going to go to 4, and this says, consider the TCP segment containing the post as the first segment in the TCP connection. What are the sequence numbers of the first 6 segments in the TCP connection, including the segment containing the HTTP post? What time was each segment sent? When was the ACK for each segment received, and so on. But we'll go ahead and look at the sequence numbers for each one of these. So sequence number for this one, this is supposed to be the first one, is 1. If you go down to the next one, it's 613. So that's the next byte that it's expecting to receive, is 613. But if we keep going down from that, hang on, let me make sure I'm doing the right one. and I am. Okay, so if you keep going down, it looks like the sequence number is 1, 1, then 13753, then 1, and that's the sixth one. So we've got our 613, 1, 1, 13753, and then back to a 1. So those are the sequence numbers for those 6 segments. And it says at what time was each segment sent. You can look over here and see what time each segment was sent. And that is marked with, let's see, that's my number 1 there. This was sent on the 20th of June 2025 at 2200 hours 14 minutes and 17.327521 seconds. So that's when that message was sent, or when that segment was sent. And if you look down, you can see that you can see the time on each one, and they change incrementally for most of these, but then you have these right here that stay the same, and those are the ones that are still their repeat acknowledgments, and if you want to see when the ACK, the acknowledgement was received for each segment, you just kind of look at the next time that the next message was sent, or the next segment was sent, and then you can see when the acknowledgement was received, because as soon as the acknowledgement's received, the message is sent back out, or another segment is sent back out. And the RTT value of each of these would be, let's see, we're going to subtract. So we'll go back to our first one. This is segment 1 for us, or sequence number 1 for us, and we're going to go to it's a push acknowledgement, and we're going to get the time here. So the time is, it's 2200 hours 14 minutes and 17 seconds, but we only went through a matter of seconds, so I'm only going to pay attention to the seconds on this. So we have 17.327521, and we're going to subtract. We're going to subtract the next one, which we probably should have done this in reverse, but we can still use this number either way. But we're gonna minus the next one, which is 17.327923, and so this would be the difference of 0.000402, and that is actually the round trip time. So that's the RTT for that first segment. And you can kind of do the same throughout and go through each one and figure out the RTT in that way. Let's see, what is the estimated RTT value after the receipt of each ACK? Let's see. If you look, Okay. Let's see. You can also find round trip time in this way too. You can pull it up through the statistics toolbar and find it that way for each individual packet. Okay, and we're going to go to number 5. What is the length of each of the first 6 TCP segments? Each of the 6 up here. So, SYNAC. PushHack, okay. So the length is shown right here, and it's 666 for the first sequence, 13,194 for the next one, 5454, 4434, and then 54 again. So that's the length for the first 6 TCP segments. The minimum amount of buffer space advertised at the received for the entire trace. Does the lack of received buffer ever throttle the sender? To figure this out, you go over here, and we're looking for window size. So calculated window size. We have 283,520 for that first one. But let's go ahead and look at this. So, all right, there we go. This is our first one, 65,280. So 65,280, 65,280. Let's see. It's 30,464. So that's much lower. 33,408. And let's look at this one. 65,280. We went back up, and we went down by a little bit to 45,056, but still, the minimum buffer space that we have would be, I think it's this segment, and yeah, it's the 30,464. So that's what our minimum buffer space is. And it looks like the lack of buffer space does throttle the receiver a bit. That's evident because the window size decreases by over half. So it kind of does have an effect there. So number 7, are there any retransmitted segments in the trace file? What did you check for in the trace in order to answer this question? Looks like we do have some retransmitted ones here. These are the ones that are in black and red, and you know that by seeing TCP duplicate acknowledgement. So that's how you know that it was resent. It's a duplicate, and it'll tell you there. And this one says the same thing right here. So these are all telling you that they're duplicate acknowledgements. Let's see, how much data does the receiver typically acknowledge in an ACK? Or acknowledgement. Can you identify cases where the receiver is ACKing every other received segment? So looks like the receiver typically acknowledges about so let's see. You can figure out how much it's acknowledging by kind of averaging out the number right here and subtracting. So we'll go over here, we'll delete that, and we'll use this packet right here first. So we'll do 139313 is the acknowledgement number. One 31313 minus, we'll minus it from this one, or minus this one from it. 134. Back over. 134,933. 4,380 is what we got there. So let's go ahead and do that one now. 134,933 minus 133,473. 1460. So let's go ahead and do one more. So 133,473 minus 132,013. 1460. So it looks like it's usually acknowledged about 1460 bytes for each one. And can you identify cases where the receiver is acknowledging every other received segment? It doesn't look like that's happened anywhere that I can see. And I didn't find it on my other capture that I did as well. So alrighty, so moving on to 9. What is the throughput? Bytes transferred per unit of time for the TCP connection. Explain how you calculated this value. So how you do this is you got to figure out your time that you used to transport to transfer the bytes. And in order to do that, you need to first have the timestamp of the last acknowledgement timestamp, which we're going to go all the way down. Looks like this goes all the way down to here. This is the final acknowledgement. And so our timestamp for this one is 2200 hours, 14 minutes, 17.548601 seconds. And since the minutes will change, or since the seconds will change, we're going to be using those. So I'm going to go ahead and enter in our seconds. So we have 17.548601. That's our timestamp for our last acknowledgement. And now we're going to get the first data packet that we sent. And so the first data packet that we sent is going to be this big push acknowledgement here. And you know it's the data packet because you've got it right here. The data, 612 bytes. That's what was sent. And so we're going to get its timestamp, which is 17.327521. So we got a difference in time there, 0.22108. So I'm going to go ahead and write that down. 2108. .22108. now that we've got that, let me make sure I got the right seconds there. Yeah, I did. Okay. So now we're going to look and see how much data was actually moved. So we're going to look at each one of these data packets and we're going to add it up. So we already know over here we get 612 bytes there. If we go down to the next data transfer, we see the next one's 4380. Let's see, plus 4380. So we've got that one now. We're going to go down to the next one. We've got 23360. Go down to the next one. 1460. Go to the next one. 39420. Alrighty. And then 5840. And 23360. $26,759. And the last one, which is a little lucky number. So we got a grand total on our data sent, transferred at 96,156. And so in order to find what we're looking for, we're going to have to divide the data by the time. And in order to do that, we're going to have to multiply the data by 8 and then divide it by the time. Because if we want our data to match up, we have to multiply it by 8 because each byte is 8 bits. So we have to account for that. And so we got our data, so we're going to multiply that by 8. And we're going to divide that by our time, which came out pretty low. And that is 0.22108. So what we came down to is 3,479,500 bits. 0.6335255493034195766 and so on bits per second. So that's how you calculate the throughput. And now we're going to look at TCP congestion control in action. We're going to select the segment in the Wireshark's listing of captured packets window, then select the menu statistics TCP graph stream. So we'll just pick a random one. We'll pick this one. And we're going to go to statistics, TCP stream graphs, and time sequence graph in Stevens. So this is what it brings up when we go to it. And it looks like you can see where no segments really moved until around 1.4 seconds or so. And so let's look at our questions here. And this doesn't really look the same as this does for me. Can you identify where the TCP slow start phase begins and ends, and where congestion avoidance takes over? So, slow start kind of begins way back here. Begins at almost 0, because there's the packet, and then it gives it some time, and then it ramps up, and it sends a lot of packets. As you can see right here, it sends a lot of packets pretty quick, and then it stops. So I think this period is definitely the slowdown, the slow start phase. This is where it begins, and then it ends here, and then you start to amass files, and you can kind of see where it sends a bunch, it pushes a bunch of data, and then it'll give it a break, pushes a bunch of data, gives it a break, pushes a bunch of data, and then spaces it out. So you can definitely see where the slow start phase begins and ends, and where congestion avoidance takes over. This looks different because in the way that I studied it, it looks more like a bell curve, kind of, or one side of a bell curve kind of going up, and then it would kind of level out a little bit, push some data, and then it would slow, and then, or then it would push a lot of data, then it would start to slow it down, and then it would drop for the measures that it's supposed to take. So yeah, we're going to go ahead and get straight into part 2, UDP. We're supposed to take a quick look at the UDP transport protocol. And in order to do that, we're going to have to do another capture. So we're going to go ahead and just start a capture. There we go. So we still got our capture going. Alright, so UDP, it's like one UDP packet from your trace, and I'm still running my trace right now. And I'm going to go ahead, I think I probably have some by now. Let's see. Yep, there's one right there. Let's go ahead and stop it. UDP, pull up all UDP files. And it's going to bring up other ones too, but when I did a little bit of research on it, it said not to use these like you would a UDP, because they are different. So select one packet from your trace. How many fields there are in a UDP header? So we got our UDP packet there. We can go down to user datagram protocol, and you can see right here, these are the items that are in the header: source port, destination port, length, and checksum. And then we're going to go to number 2. By consulting the displayed information in Wireshark's packet content field for the packet, determine the length and bytes of each of the UDP header fields. Each one in bytes is only 2 bytes, and that's pretty uniform for that. And I mean, like, as you can see, nothing exceeds really 2 bytes worth or 16 bits worth of data there. The value in the length field is the length of what? The value in the length field is the total number of bytes. That's the bytes in the header and the payload, the data payload. And you can see the length right here, 43. So if you subtract 8 from that, you get 35 in data. So there you go. Your header takes 8 bytes. Your data payload's 35 bytes. Let's see, what's the maximum number of bytes that can be included in a UDP payload? The maximum number that can be included in a UDP payload is going to be the most you can send in a packet is 65,535 bytes. So if you're going to have to take the header off of that, and you'll have to take the IP header as well off of that. So that's 8 from the UDP header and 20 from the IP header. And once you take that 28 off, you're left with 65,507 bytes. And that is the max UDP payload. Let's see, what's the largest possible source port number? Source port number, largest one that you can have is 65,535. 6. What is the protocol number for UDP? The UDP protocol number is 17. And let me see. You can find that under Internet Protocol version. Let's see, UDP. There it is. Protocol UDP 17. So you can find that right there if you need to look that up for any of the other protocols. The reply. Let's see, the last one. Examine a pair of UDP packets in which your host sends the first UDP packet and the second UDP packet, and a reply to the first UDP packet. For a second packet to be sent in response to the first packet, the sender of the first packet should be the destination of the second packet. The relationship between the port numbers and the two packets. Basically, the reply packet uses the source port from the first packet as its destination port. And that's kind of how that swaps over. And the source port from the first packet becomes the destination port for the second packet. And the source port is the second packet when it sends it back to the first. So that is how those relationships would work. And that looks like end of lab 2. So thank you.